So as we go to look back at what we've been up to over the last while, really probability for me is about this formula, which I go on and on about every lesson, where I say, how many possible outcomes are there and how many favorable outcomes are there? And for me, that's really the probability equation. But in order to visualize the possible and the favorable outcomes for any particular event, we need tools. And the tools we've learned about are the Venn diagram, the tree diagram, and today we're going to talk a little bit about the two-way contingency table. Now, we also have some identities. The one is the addition rule, which says the following. And then this can be simplified. If you've got two mutually exclusive events, there's no overlap, then that rule just loses the and part and it becomes even simpler. And we also have the complementary rule, which we need to kind of keep with us as we go. Now, the other one for today is if we know events are independent, we can multiply their probabilities in order to get the probability of, this A and B happening. Or another way we can use this independent events identity is if you want to check whether events are independent, you find the probability of A, you find the probability of B, you get what that is, and after multiplying, and you check it's the same as the probability of A and B occurring. It sounds a bit weird when I say it like that, but when you see it in an example today, it'll be much easier. Okay, give me a thumbs up if this stuff looks vaguely familiar. I know that the new stuff, obviously, we're going to talk about today is this and that, but does everything else look vaguely familiar to you? Okay. Awesome. Well, let's rock and roll. So we'll come back to this identity equation a little bit later, but let's just start with reading a two-way table. So here is a two-way table. And what a two-way table has is it has information and it's split up. So this is a year 7 class. And on the horizontal, we have two mutually exclusive events, the event of being a boy and the event of being a girl, right? They're mutually exclusive. If you're a boy, you can't also be a girl, etc. Then on the other one, we have vertical columns, and that is about, well, let's do this. If this is about gender and the two choices here, this is about favorite sport, which splits into 3. And you can either have football as your favorite sport, athletics, or other. I want to know how many boys chose athletics as their favorite sport. So we look at the table and we find boys and we find athletics and we get 4. Okay, what was the most popular sport with boys? So again, we look for the row with boys. We see that 10 is by far the biggest number. And so that must be football. So what we're learning here is we're learning how to read information from a two-way table or a contingency table. Next question, how many girls are in the class? How many girls are in the class? Well, this is where having some totals might be helpful in our tables. So it's often with tables, instead of just having the actual items, we have what are called totals. And the girls row would total up to 16. So let's go. How many girls in the class? There are 16. 5 of them like football, 4 like athletics, 7 like something else as their favorite sport. How many pupils are there in the class? So I'm going to total up my boys. And then I'm going to total up both genders and I'm going to get 31. Yeah. And if I said to you, out of the year 7 class that you have information on, how many students' favorite sport is athletics? So how many students' favorite sport is athletics? So I go to my athletics column and I get 8. And you know what? I'm so tempted by these other ones. I'm also just going to fill them in. That's going to be 15. That's going to be 8. The good news is that 15 plus 8 plus 8 gives me 31. 15 plus 16 gives me 31. And, you know, this makes a lot of sense. Okay, so the basics of doing the table, not hard. What if I said to you, what is the probability, if you choose a random person from this class, what is the probability that that person is a boy? So if you randomly choose someone from the class, you don't know, you just sort of tap them, you know, or you choose a desk number and you go to that desk, what's the probability that a randomly chosen person is a boy? So clearly there's 31 to choose from, and 15 of them are boys. So it's just below 50%. Okay, so that was giving a bit of attention to the horizontal rows. Let's say this, what is the probability if you choose a random person that their favorite sport is football? So what is the chance that someone's favorite sport is football if you choose someone randomly from the class? Oh, well, that's kind of nice. It's 15 out of 31, but for a different reason, because it's that. Okay, what about if I said to you, what is the probability if you choose a random person from the class that they're both a boy and the symbol for and in probability, or let me just use and their favorite sport is football? So what do you think the probability that a randomly chosen person is a boy and their favorite sport is football? So where are we going to go look? Look for boys, we look for football, and there are 10 students. So only 10 of them would be a favorable outcome for the question boy and football. Okay. Now, from what I can see, let's just do a quick vote. Thumbs up if you found that okay. Thumbs down if you didn't find that very, like, you know, not good or something like that. Okay, so now let's connect this to the idea of independent. So is gender independent of favorite sport? Well, at the beginning of the lesson, I said to you the definition for independence would be something like this. We need to check that this is true. But now A and B are just placeholders. So instead of saying A and B, what I'm going to do is what makes more sense for this question is I'm going to let B be boys, and then I'm going to say that is F for favorite sport of football, and then I want to check whether or not the probability of this times the probability of that is the same. I don't know, but give me a thumbs up if you understand how I'm connecting the A and B thing to B and F for this particular question, because we were dealing with boys for gender and F for favorite football. So you can feel the connection. Okay, now, if I look at the decimal version of this, let's do this. So probability of B and F, let's put it into decimal because it's a little bit easier to deal with. So I get 10 divided by 31, and I get, if I round off to 2 decimal places, I get 0.32. So just check that you get that as well. And then I want to try and go probability of, what was it? A B. So let's just go times probability of favorite sport being football. So 15 over 31 times 15 over 31. What do we get for that? because I need to check whether this equality holds. I get 0.23. So here's something interesting. Is the probability of B and F equal to the probability of B times the probability of F? Can we say these are equal? Are these two things equal? No, they're not, because 0.32 does not equal 0.23. And so therefore we say, we would say here, gender is not independent of favorite sport, or we just say, therefore, they are not independent. Okay, and then you could even say, the particular thing you're dealing with. But the main idea I wanted to check was you understood how to connect this general thing to a specific situation. Now, it gets much easier if we do another example. And so let's do another one, because I think that way it will become clearer. All right, but you did well there. So here is another table. All I want you to do is I want you to calculate the answers for these 4 questions for me. So put the answer in the chat. I'll let you read the table. It's dealing with the hair color of 50 learners. And it's basically, you could do a thing like this in your class, and you could go around and draw up your own two-way table. This idea is very understandable, but let's just work with what we've got for now. So K-lead, let me have a look at what you're saying. If we look at the probability of football, no, it wouldn't be, it would be 15, because you look at the column of football. So 15 out of the 31 have football as their favorite sport. Does that help, Kelly? So you look at the whole column, because you're looking at F as in, yeah. But good question, Kelly. I think you helped a lot of people there. Yeah. So that's why I love questions, because often many people are thinking the same thing. Okay, let's do 1 to 4. Okay, so in Corsi, why was the denominator of the probability of number of boys who like football 31? Because 31 was the total in the whole class. And so because there were only 31 people in the whole class. Okay, so here, the total in the whole class is 50. And so for the first one, it has to be out of 50. And it says brown hair. So brown would be 17 out of 50. And to be honest, the next one's going to be out of 50 as well, because it's still, you're choosing a random learner from the class. So blonde hair, I look for blonde. And it's so nice. They've even done the total already for me. So there's 11 students who have blonde hair. So there's 11 out of 50 chance you choose someone with blonde hair. Now, the next ones are interesting, or a little bit more interesting, because they have an or. So the or means the favorable outcomes could be bigger. It could be this or that, or, It's still going to be out of 50 for both of these. So what do we think the answer for 3 is going to be? Well, what are the favorable outcomes? There's black hair, which is 22, or brown hair, which is 17. So what are favorable outcomes? Well, there are 39 favorable outcomes. Yeah. And what about, we'll have blonde hair or brown hair or black hair. Well, I guess then all 3 of these. So that would be 39, that would be 50. And there's actually 100% chance that someone will either have blonde hair or brown hair or black hair. And that makes sense because that is the whole table, right? That is that's every possible combination or probability of 1. Okay, so that was the sort of easy stuff. Maybe now we want to check whether or not gender is independent of hair color, right? So we have gender up here, and that's split into boys and girls. And then we'd split over here, this is hair color, and that's split into black, brown, and blonde. Now, there's a couple of different ways we can do this. We can deal with girls and black hair, we can deal with boys and brown hair, but we have to just be consistent. So what I'm going to start by doing is I'm going to say, what is the probability of somebody having black hair? So what is the probability of someone having black hair if you choose them from the whole class? What is the chance of that? So it's going to be 22 out of 50. Well done. Exactly. Now for this next one, we have a choice. We could use boys or we could use girls. Which one would you like to use? I don't mind. There's 2 ways of doing this, but whatever we choose now will affect what's on the other side. Okay, let's choose girls. Okay, what is the probability of randomly, if you choose a random person in the class, if they're a girl? It's going to be 24 out of 50. Yes. Okay. So you've dealt with the rows, you've dealt with the columns. Now, what you need to do is you need to work out, if you think about checking whether these things are independent, you need to find what is the probability that a randomly chosen person has black hair and is a girl. So what do you think the probability of that happening is? We're still going to be out of 50 because there's only 50 people in the class. Remember, black hair and is a girl. Well, we go and we find black hair, we find girls, and we've got 10. Cool. So now to check for independence, what we're going to do is we are going to say, what is the, and I'm going to use my calculator, and decimals tend to work better because it's easier to compare. So 22 over 50 times by 24 over 50. And I don't know if you agree with me at home, but check it. I get 0.21. Okay, I'll round off to 0.21. What do we get here for 10 over 50? We are going to get 50. Well, that is going to be 0.20. Okay, now I think that is close enough that you can say they are equal. There is a little bit of ambiguity, but for me, this is one decimal place thing. So these are, I mean, yeah, I would say that one decimal place is fine here. And so we would say, therefore, they are independent. because these are essentially the same. Everyone, give me a thumbs up if you followed that logic. Give me a thumbs down if you didn't follow it. Okay, let's squeeze in one more before the break. Let's squeeze in one more before the break. So this is straight from an old exam question. See if you can do this whole one for me over here. You're given 80 learners in grade 11 were asked whether they played sport for their school, and the results were recorded in the following contingency or two-way table. See if you can answer those 5 questions and then just pop them in the chat as you do them. Each time you see a table, it gets a bit easier to read off the information. Okay, so A is going to be 50 out of 80. What is B? I suppose play sport column is 48. And what do we have for D? So D is just going to be 50 . So I'm going to go back and put C in terms of decimals because it makes life a bit easier to compare them if they are in decimal language. So do we think that sports preferences are independent of gender? Why or why not? What do you guys think? What do we need to look at? What are we comparing? Do you think sports preferences are independent of gender? What do we need to check? Well, I think we need to check, is the probability of being female and the probability of playing sports, is this the same as the probability of F and S? And I think we may have worked that out already. So female and play sport was C, which is 0.26. And female times play sport was D, which is 0.375. So are these independent or are they not independent? They are not independent because, yeah, this equality doesn't hold. And that's all we have to check, you know, if we want to know if they're independent, the equality holds. If they're not independent, then it doesn't hold. Give me a thumbs up if you're following what we're doing. Give me a thumbs down if you're feeling a bit unsure in the chat, just so I get a sense of how everyone is doing. Yeah, awesome. Okay. Well, I think it's time for a break. We've done half an hour of solid maths, and we can take care of our brains, and then our brains will take care of us. So just stand up, give your body a little stretch. Oh, that feels good. Let's roll the shoulders back. Stick that chest out, stomach's in, and chest out. Roll the shoulders backwards, and roll the shoulders forwards. And let's do a little bit of rotating. So just to start with a little bit, and then as you relax, you will see that you get a bit further. Oh, lots of clicks. Okay. And then let's do a tricep stretch. Do that. And then let's do the other side. Okay. Stretch our necks to the one side, to the other side. And then let's just shake out our arms, shake out our legs. Okay, and then let's do some cardio. And let's do 20 air skips in 3, 2, 1. Halfway. 5 more. And that is our little bit of movement, just to let our brains unwind a bit. And then I want you to try and solve these Maths 24 puzzles for me. The glory can be yours. Let me know in the chat as to how you think you would do these Maths 24 questions. Okay, Dimo Sanawe has got the first one. Oh, wait, no, there's 6 times 2 times 2 times 1. You've got too many 2s. 6 minus 2 is 4 times 6 times 1. So that's one way of doing it. Andile, I agree. How else could we do it? Or maybe a blue or yellow one. No problem, no problem. We always look for the bar at the bottom. The bottom bar tells us the bottom of the number. What about the blue and yellow? Andina is on fire tonight. 7 times 3 plus 5 minus 1. Does that work? I don't think it does, because that's 21 and that would be 4. So close, but not quite. Toboko, these are both 6s. So there's no 9s there. Those are both 6s, I'm afraid. Letabo has said 1 plus 2 gives us 3. 3 times 6 gives us 18, plus 6 is 24. Yes, very nice. Well done. Anybody know with the blue or the yellow? I was thinking for the blue one, couldn't we go 7 plus 5 to give us 12? What could we do from there? Who feels like they knew? So 7 plus 5 times by 3 minus 1. So that's 12 times 2. Aha. Yes, I see Tebogo has got the yellow, and sorry, Emmanuel's got the yellow. 6 minus 4 gives you 2, and then 8 minus, sorry, what's going on? 8 minus 2, where did the 2 come from? Oh, you got the 2 from this. So 8 minus 2 gives you 6, and then 6 times 4 gives you 24. Yep, agreed. 2, 8, yep, that's fantastic. Okay, cool. Everyone, let's return to our lesson. So let's try and do this question. First question, are the events, so it says here, each of the 200 employees of a company wrote a competency test. The results are indicated in the table below. And it says males, females, pass, fail. Are the events pass and fail mutually exclusive? So explain your answer. Oh, I'd love to hear from someone on the audio here to maybe explain, or otherwise put it in the chat. Are pass and fail mutually exclusive? What does mutually exclusive really mean? Aha, and Dile, you have nailed it. Yes. Pass and fail are mutually exclusive. You can't pass and fail at the same time. There is no intersection. So the technical way of saying it is the intersection between pass and fail is equal to the empty set, or you cannot pass and fail at the same time. And because they can't exist at the same time, they are mutually exclusive. So yes. Okay, next question. Is the competency test independent of gender? I want you to try and do this by yourself. Where would you start? What would your first step be if you wanted to compare gender to test results? Where would you start? There's a couple of ways you could do it. I want students of the room, and you can put your hand up and tell me, it might be quicker, or you could put it in the chat. What's my first step? Okay, I see a hand is up. So let's unmute Sate. What's your first step? So Sate, can you hear me?
Oh, so my first step, I'm going to find the intersection between female and pass.
And pass. Okay. So
yes.
What is your denominator going to be?
200.
Absolutely. What is your numerator going to be?
72.
Perfect. Love it. Okay, now what else do you need to find?
I'll multiply the number of females and then
But it's not number here. It's going to be the probability of female and the probability of passing. So what's the probability of being a female in this group?
It's 122.
Perfect. Yep. And what's the probability of passing, of somebody passing in this group?
It's 118 over 200.
Perfect. Okay. You have done lots and lots. So I'm going to get another person a chance, but thank you so much. That was very helpful. So now what do we need to check next? Well, I suppose I should go, what is this times this going to be, and I'm going to use my calculator because, so I get 122 over 200 times by 118 over 200. And we are going to get 0.359 or 0.36. And then I also want to know what is F and pass going to be. And that was just 72 over 200, which as a decimal would be 0.36. And so we can say, yes, independent. And the reason is because these two are equal to each other. Okay. Thumb up if you followed all that, thumbs down if you felt a bit lost there. Now, when you say independent, you must just write this last bit where you say this is equal to that. You've shown that. That's why you know it's independent. Okay. Cool. Let's do this one. These are just common exam questions. So I want you to find, I want you to do the whole question. So first tell me what A and B is. And then I want you to know what that is, and what that is, and what that is. So off we go. See if you can do it using what you've learned in this lesson so far. So there were 100 boys, which meant that if that's 100, this has to be 20. So I've used that information. And 60 girls. So there's that. And then this would be just adding up. So 128. So A is 20 and B is 128. Okay, what about 1.2? Are the events being a male and did not watch TV during examinations mutually exclusive? Give a reason for your answer. What do we think about that? Are they mutually exclusive? Are they not? Why not, Lorato? I agree with you. So it is no, but why not? Well, if I look at my table and I look for male, you can be a boy and not watch TV during exams. Exactly, Lorato. I could not have said it better myself. So no, and I would even say, did not watch TV during exams. There are 20 boys who did not watch TV during exams. So if we look at that, the table tells us there are 20 boys who did not watch TV during exams. So these events cannot be mutually exclusive because there's 20 boys who did both. Okay, if a learner who participated in the survey is chosen at random, what is the probability that they watched TV in the period in which the examination was written? So what's the probability that a randomly chosen learner watched TV during the examination that was written? Where am I going to look? I'm going to look at rows. I'm going to look at columns. So there are 128 people watch TV. How many were there in total? There were 160. So there's a 128 out of 160 chance. What is the probability is not a male and did not watch TV in the period during which exams are written? That sounds a bit, is not a male is another way of saying a female. So that you just have to watch, the not male is a female. What is the probability that a female did not watch TV during the exams? So it would be 12 out of 160. So, the reason this is smaller is because of the word and, because to be a female or not a male and did not watch TV, that's a smaller subset. So it would be 12 out of 160. Okay, that's great. Good. I want to find a different type of question for you now. That's easy enough. That's also quite straightforward. Let's do one like this. This looks a bit different. It's like a table. It hasn't got a table, but it's still related to this type of question. So you are given the following question. Calculate for me the probability of A and B occurring. And this time, all you're given is the stuff above it. So I want to know from you, where do I even start? What bit of mathematical theory might be helpful? Why is this trickier than before? What makes this hard or more difficult than the ones you've been doing so far? Lorato, you know what's going on. Okay, the reason it's a bit harder is you need to, this is a general identity called the additive identity. And what this will need to know is this. Now, how many of these do I have? Well, I've got the A or B, I've got the A and I've got the B, but I don't have this bit. But I know this should be 0.6. I know this should be 0.5. I know this should be 0.2. But something's not quite right here. What does this little bit at the end have to be in order to balance the world? Well, the only way that this will be equal to 0.6 is as if this is minus 0.1. And so we know that this must be 0.1 or 10% or 1 in 10. Those are all the same. Okay, now, are the events A and B independent? I want you to check for me. How would you do that? What would you need to do? What would you need to do? Are they independent? Are they not independent? What do we think? What do we need to check? So I think I want to find out what that is, which is 0.2 times 0.5. And that should be 1 out of 10 or 10%. And I already know that the probability of A and B is 1 out of 10 or 10%. So are they independent? So we can say A and B are independent. And the reason they're independent is because, I'm running out of space here. Let me get rid of this. We know that P, A, and B equals P of A times P of B. And that's it. Okay, let's see how much time we have left. We have time for one more question, guys and girls. Are there any questions about this one before I move on? Let's give a moment. Okay. Let me find one that is a bit more. Let's do another one like that one, because we've done lots of the table ones today. So let's do this. So there's my question. You are given two events. Are the events A and B independent? Justify your answer with appropriate calculations. This is actually not too difficult. But let's just see if you can do it. So I want to know which gives me 0. And then yep, that was actually super simple. So I think that is that. You know what, guys, we can actually call it a night for tonight. I think we've done well. If we look back at what happened in the lesson, we looked at reading off two-way tables and how two-way tables are just made of mutually exclusive events. We learned how to read out information. We learned how to find missing information. And we also learned how to check for independence. Okay. And so that is that for tonight. We've done 6 lessons on probability this year. We did 8 lessons on probability last year. And so if you need a bit of a top up, don't be afraid to look at that. We also have quizzes on probability that you can do. But that is it for now until exam revision for probability. We start the unit on financial maths on Monday. Okay. And then I see here, Kia has said, please get the quiz link on the Watobe app or look at the Watobe website and just log in. And yeah, I hope that you enjoyed today's lesson. Are there any final questions before we call it a night? Any comments from the people of the room? What part of probability do you think was the hardest? I'm always interested to know. Night, Kia. Thanks very much. Venn diagrams. Oh, Flumelo. Okay, so Flumelo, what you can do is you can log into the Watobe website. And if you log into the Watobe website, you should also be able to get the quiz link that way. Okay, Nompilo says finding if events are independent using the table. Lorato says the 3-circle Venn diagrams. Okay, cool. Okay, so what we want to do then is if you go to the Watobe lessons, what I would suggest doing is if you look back at previous lessons, you will see that last year we did probability for 8 lessons, and you can go and look at a whole bunch more Venn diagram questions. And I also included I'm also including another Venn diagram question in today's quiz. So what counts more out of 100, probability or finance? Tato, it depends on your teacher's test. When you get to exams, probably about the same weight. Finance and probability are about the same.